This is an intimate list of 36 authors as listed here, and it's a contribution across many different national labs, universities, and companies. The context of Impeccable is in the drug discovery domain, which, as many of you know, is a highly computationally difficult and expensive process. In practice, it takes approximately 10 years and several billions of dollars to design a single drug. And the fact that there are so many drug candidates just makes it impossible to do an exhaustive search. Consequently, the need is for sophisticated and intelligent computational processes where the performance of multiple stages is used to try to filter a large number of not so promising drugs, i.e. advance-only drugs that are very promising, as shown in this schematic on the right-hand side, where each subsequent stage is obviously more computationally expensive, but obviously more accurate, and therefore you only advance a small subset. The hope is that this pipeline of multiple different methods will give us greater ability to utilize our computational resources more intelligently and thereby come to a optimal selection of a drug candidate. This has been the underlying paradigm of high throughput virtual screening for a while. However, it's valuable, but it has clearly not been enough. And one can see that each of these stages is being enhanced by the use of machine learned approaches through surrogate models and other approaches, so that each stage gives you the same scientific output, but charges or costs less computation than a quote unquote vanilla method. So all of this put together gives you a enhanced pipeline. And this work came together across many teams at national labs in the context of the National Virtual Biotechnology Lab, which was set up by the Department of Energy in response to COVID. And there are many facets of the NVBL. We, as the Impeccable team, were responsible for the part in boldface, namely supercomputing and artificial intelligence for design of targeted therapeutics. And we were fortunate and honored to receive a distinct prize from the US Secretary of Energy. Okay, so as I mentioned, this is the paradigm of high throughput virtual screening. The impeccable incarnation of this pipeline involves multiple different methods, and three or four primary methods involve what we call independent workflows. The first workflow is high throughput ensemble docking at very large scales, and this is to identify promising candidates, which are called hits in the community. The second is to take these hits and to use physics-based simulation methods, but ML enhanced, to try to improve an understanding of their physical properties and thereby the mechanistic changes when they bind, and to use this information to perform the gold standard in the drug discovery domain, namely binding free energies, but now only for those that are very promising in terms of the mechanistic binding properties. So at each stage, you're performing more accurate, more insightful calculations, but on a fewer set of candidates. So you go from a very large space to a small space. What are the computational challenges? As mentioned, this has been a paradigm for a while. We've obviously innovated at the individual methods that I mentioned, workflow 1, 2, 3, and 4. Don't have time to talk about the details, but computationally speaking, what is the challenge in supporting the methodological innovation? Well, there are many, but let me focus on heterogeneity of both the workloads and the resources on which these workloads have to perform. So the table at the bottom just tells you that every major supercomputer in the United States and even Europe was employed. And I think you get a sense of the architectural node and obviously software variation across these machines. But in addition to that, the workloads themselves are very, very different across the different workflows. The workload, namely the set of tasks that are to be found in the first workflow, are a set of docking function calls, whereas the workflows for binding free energy are traditional large number of simulations of the MPI type. And in between, you have a mix of machine learned methods, models, and simulations running together. So you've got this portfolio of different tasks that have to be managed together. So that's probably the important challenge that we want to emphasize here. And in addition to that is the fact that the calculations themselves vary significantly from drug candidate to drug candidate, or for drug candidates to different receptors, where a receptor is a part of the target protein where a drug candidate binds. And so the graph on the left-hand side shows you the time that it takes to take a library of about 6 million drug candidates and go through each of these 6 million on different receptors. There are 32 receptors so in this particular problem, and you can see a broad distribution. But the figure in the middle, the long tail, shows you that for any given receptor, the different drug candidates also take a lot of time. So you've got to manage this very large workload at very large scales as a matter of the entire machine, but each calculation is highly long tail distributed, so clearly a load balancing challenge amongst many other things. And just to put this into context, we developed a capability called RAPTOR, which uses radical cyber tools, which in turn are a set of building blocks for workflow middleware. And we were able to, on Frontera, for example, using essentially every node, every core of Frontera, that's about 8,000 plus, achieve up to throughputs of 144 million docking calculations per hour. Now, this is a factor of 2 more than any published docking throughput rate, either on supercomputers or on clouds. So just to give you a sense of the scale at which we're operating. Similarly, the sense of scale for other parts of the pipeline. This is workflow 2, where you have machine learning models guiding the large number of ensembles and molecular dynamic ensembles. The bottom right-hand table gives you a sense of the scale, the number of GPUs used, 6,000 plus on Summit. And this obviously, as the graph on the top right-hand shows, leads to several orders of magnitude improvement over vanilla simulations. So again, you see a combination of the methodological innovation with the scale at which these methodological innovations are being implemented. And this is to tell you that workflow 3 and 4 about the binding free energy used radical cyber tools on Summit, and lots of details here provided in paper, as well as references therein, that we're able to use every core, every node of Summit, both the CPUs and the GPUs, to concurrently run workflow 3 and workflow 4, 2 different types of binding free energy calculations. Again, you get a sense of the scale at which we're able to operate unprecedented. And to kind of tell you what all of that computation leads to in terms of scientific capabilities as well as impact, you get a sense of the number of docking calculation, 100 billion, again, larger than anything published as far as we know, tens of thousands of binding free energy calculations, again, amongst the most that we were aware of, and the peak performance at about 8,000 nodes on Frontera and 4,000 on Summit. And all of this has led to scientific insight as well, as captured on the right-hand side, where we have a actual drug candidate that has both had experimental validation and is being synthesized as being a very promising antiviral drug candidate. And more details can be found in a separate paper that's linked at the bottom of slide 9. Okay, so in some ways I've talked about the performance and the impact of each of these stages distinctly, but in practice, what we really want to do is run these together, one after the other, so that you have a pipeline that is really a single campaign running concurrently, all these stages. And the reason why you want to make sure that these methods are working together is captured in this figure on the left-hand side, where the red bars show the binding free energies. If you don't seed the binding free energies with a what we call workflow 2, a machine learned driven MD simulations to try to improve these sampling and the phase space coverage. Now, in the graph, lower is better, and you see that red, which represents standalone binding free energy calculations, is typically and statistically always higher than the black dots, which represent different situations of the same calculation, but start with different starting structures as identified by the simulations in workflow 2. So you see that when you run this as an integrated pipeline, you do get better scientific results. There's more details in the paper. So in addition to the heterogeneity, you can see that putting them all together, all the stages together, introduces an additional set of challenges. I don't have time to speak to them in detail, but just get a sense that you end up with having to couple stages that are and methods that are 7 orders of magnitude different in the computational cost, as you can see. Okay, so thank you. In summary, I want to say that we've made significant advances in the first generation of infrastructure to support the drug discovery pipeline. As the methods evolve, so will the infrastructure. And there are multiple systems and software challenges that Impeccable has addressed and needs to address more, 2 of which are mentioned here. Thank you very much.